Okay, in this video we're going to see if I can actually take some things you guys have been working with and put a few things together to sort of show you how they work. Now, here we have a set of parallel plates, okay, and let's go with some positive negative plates here, okay, and let's go with this being a positive plate. We'll say that one's positive. Let's say this one is negative, okay, and we're going to bring in a charge. Okay, so here's a charge, a little positive charge, maybe a proton or something like that. And we're going to have it come in from the side. We're not going to have it inside the plates or have it come in from the side. Now, obviously, between these parallel plates, there is an electric field that would go down something like this. So when that charge would come inside those plates, it's going to come in, and as it goes through, it would get pushed down. Okay, so it's going to get pushed down a little bit. So it's not going to go straight, it's going to get pushed down. All right, so in this setup, we have an electric force on it, and if we find that, we have the electric force is equal to QE. You've done this before, and in this circumstance, it would be going down. Okay, now what we're going to do though is we're not just going to use an electric field, we're also going to use a magnetic field. And suppose I have a magnetic field, and I have the magnetic field and it looks something like this. There's my magnetic field. Now, there's also going to be a magnetic force. So you have your FB is equal to QVB, and sine theta is going to be equal to 1. We're not going to worry about that. And if you use your right-hand rule, your shooting finger is pointing to the right, your field fingers are going into the screen, and your thumb should be pointing up. So that force would be up, and these are opposite forces for a reason. So we got the electric force going down, and we have the magnetic force going up. And what we want to do is we want to take these two forces, and you want to make them equal to each other. All right. So if we do that, Q times E is going to be equal to QVB. And since the electric force is down, the magnetic force is up, and the two forces are equal, well, the tiny little q is just going to go straight through, which seems kind of stupid. Like, why would you ever do this? Well, there's actually a reason why they do this, and they do this all the time. And I'm just going to get rid of my little labels here. I'm going to use this area over here. There we go. Because what you can do is you can set up a barrier on the other side. So let's give me a little rectangle tool or whatever, something like that. What you can do is you can set up a barrier on the other side, something like that. And then let's fill it in like that. There we go. Except what you do is you have a little hole in it, something like this. All right. So the particles can hopefully go through that little tiny hole. Now, why would you do this? Well, if we go back to the green expression over here, we got QE is equal to QVB. And of course, the Q's cancel out, and we're left with E. The electric field is going to be equal to the velocity times the B. And if we just rearrange this to solve for the V, we have the electric field divided by the magnetic field. And this is used to calculate the speed of subatomic particles. This is called a velocity selector. And it's called a velocity selector because it selects charges by their velocity, because only charges with a very specific velocity or speed will actually go straight and go through the hole. So suppose the particle is going too slow. If the particle is going too slow, the electric force doesn't change, but the magnetic force becomes weaker. So the electric force stays the same. It's going too slow. Since the FB relies on the V quantity, it gets weaker. The electric force sort of wins, and the particle would hit down here and hit the barrier. If the particle is going too fast, FE stays the same, FB gets stronger, FB wins, shoves it up, and the particles are going too fast, hit up here somewhere. So only very specific particles going the exact speed that you need will actually go straight and make it through the hole. So if particles are going through that hole, you know exactly how fast they're going without actually having to actually calculate or measure it. Because measuring speeds of these things can be unbelievably difficult. It's way easier to do something like this. Now notice it has absolutely nothing to do with the charge, because the charge canceled out. So it could be a proton, it could be an electron, it could be an alpha particle, it could be any nucleus you want. It makes absolutely no difference. The charge cancels out. It's all about how fast it's actually going. Okay, and this is what's called a velocity selector. So it's a really, really, really simple idea. Okay, and it works really, really well. Now, what is this used for? Well, this is used for tons of different things, but more specifically, these are used especially for like particle accelerators and stuff like that, or different machines where they need to know how fast the particles are going so they can actually analyze what they're actually doing. Now, of course, you can go beyond this a little bit, and you can actually do other things as well. For example, they can take things like this, and they can increase or decrease the magnetic fields or electric fields to get them to either curve up or curve down. And the thing is, if they actually start curving down, I'm just going to draw it over here. If they actually curve down something like this, or curve up something like this actually becomes projectile motion. And then you can incorporate projectile motion into subatomic charges and calculate different things. It's not actually that hard to do, and you actually can get some cool things out of it. But if we sort of connect this to what you guys did before, these plates over here, this actually becomes your range. Remember that from projectile motion, your distance in the x direction. The v comes in here. This is actually your vx, which doesn't change. You can use your Vx and your range to find out the time in between the plates. You can then use your two forces, your up force, your down force, to find your net force. With net force, you can find acceleration. Of course, with projectiles, your acceleration was always gravity. This has nothing to do with gravity. So you could use those two forces to find your net force, to find your acceleration. With your time and your acceleration, you can find your change in Vy and do all of the projectile motion stuff that you guys have done before. Okay, but we're not going to worry about that with this video. That's something we can do sometimes in actual class to show you how that works. And really, it's not difficult at all. Once you do the F equals QE and the F equals QVB, it's just F equals MA and your basic projectile formulas, and that's it. Okay, so it's actually pretty straightforward. It's actually pretty easy compared to some other stuff you guys have done. But we're going to focus on this part right now. So this is a velocity selector. This is how it works. So, for example, suppose we had an electric field. I'll sort of make something up here. We had an electric field of 7,000 newtons per coulomb, and let's say the magnetic field was 4.6 Teslas, and we want to know how fast this thing was going. Well, the velocity is just the E divided by the B. We have the E value, we have the B value. All we have to do is just divide those two out, and we will have the actual velocity of the particle. So we've got the 7,000, we just divide that by the 4.6, and we have a V of approximately, well, give or take around 15,200 meters per second. So only particles going 15,200 meters per second, not 50,200, 1,520, one too many zeros in there, let's fix that a little bit. Only particles going 1,520 meters per second will go straight through, go through the little slit or the hole, the little filter there, and make it to the other side. So that's it. So anything on this side is going 1,520 meters per second. Okay, so that's what the idea behind a velocity selector. So let's sort of show you what these things are actually used for and how you can actually apply them. Okay, so I'm just going to show you a little something on these guys and how they actually can be applied with particle accelerators, and then we'll get to practicing some simple stuff a little bit later on. So basic particle accelerators, most of them, a lot of them start with velocity selectors, and this is what we were showing you before. Charge comes in from one side, you got a magnetic field, you got an electric field called a crossed field setup because the fields do cross across each other. And as you can see, we've got the electric force going one way, the magnetic force going the other way, make these two equal so the Q's cancel out, and then it's really easy to solve for the V. Okay, this was actually first really used by Thomson in 1897. This is a guy you took in grade 9 science. He's the guy, of course, who found the electron. And inside of his apparatus, there's the two electric plates, A and B, above and below. And then on either side, on the outside of his tube, and this is a cathode ray tube, good old grade 9 science, he had Helmholtz coils, or 2 magnetic coils on either side to make the magnetic field that goes across. And then he bent the beam up and down to see if he could find the charge to mass ratio of the electron, which of course he did, and he proved the electron existed. And of course, this is a picture of the actual tube that he actually used. You can actually see the little tiny metal plates inside of it. Okay, now for more modern applications, one of the main ones is a mass spectrometer. And a mass spectrometer idea is actually pretty simple. If you start in the top left-hand corner, this is where the velocity selector would be. The particles are going through, and they go through a slit. And if they make it through that slit, every single one of those particles, even though they're different particles, they have to have the same speed. And then what they do is they go through another magnetic field. And that magnetic field over here, towards the right, actually causes them to curve their path. And you can see they're hitting in 2 places. These red ones are heavier, so they're harder to curve, so they go straighter. The blue ones are lighter, they're easy to curve, so they curve more. So they know all those particles have the exact same speed, but the heavier they are, the harder they are to curve their path. So the more they curve, the lighter they are. And this is how they get the masses of subatomic particles and things like nuclei and all that type of stuff. And this is how they get atomic mass. So this is where all the atomic masses come from on the periodic table. See, it has nothing to do with chemistry. It's all about physics. So here's another good example. So you can see on the left side here where the source is, that's where the velocity selector would be. You got a couple slits. That big horseshoe-looking thing is a giant electromagnet, bends the beams, and these are all neon nuclei. And you can see that there's 3 distributions because there's different isotopes, and this is how they will spread and separate isotopes. So the neons with a mass of 20 are easier to bend, so they're tighter into the circle, where the 22s are a little bit further out, and this is how they get the distributions of the particles. So that's why the atomic masses on periodic tables are decimals, because they show the average of the isotopes. So if you have like a pretty even split of isotopes, you know, like between like 200 and 201 for a mass, well then that's why the periodic table is like 200.5-ish or so. But if it's really close to the whole number, that's because most of the stuff hits by that whole number. Okay, these are some pictures of some mass spectrometers. There's one right there. Here's another one. You can see the curved path going around. There's the horseshoe magnet over there. And these are a couple guys from the U of M who work on this type of stuff. The guy on the left is actually Professor Entz, and he was my quantum mechanics professor. There's also cyclotrons. Cyclotrons also use mass spectrometers in order to get a beam of particles, and they are used to accelerate particles. And they sort of use electric fields to make particles go faster and slower, and they use magnetic fields to change their paths. And here's a picture of the Triumph particle accelerator in the States. That's a cross-section of it. You can sort of see how big it actually is. And of course, the CERN particle accelerator is the really famous one in Europe, between France and Switzerland, which of course this is where all the crazy research is done. They make mini black holes and trying to find the Higgs boson, all that kind of stuff. That's where all this type of research is, and this is where, of course, Sheldon Cooper would like to work, but that's what is going on there. So that's what a cyclotron does, is uses electric fields and magnetic fields to either accelerate particles or redirect particles, and it's really kind of neat how that type of stuff works. But the mass spectrometers are actually used to find the masses of isotopes and nuclei and subatomic particles, and it's really cool just using basic velocity selectors and electric fields and magnetic fields to redirect them to sort of show how they actually work. Okay, so we're going to do a little practice with mass spectrometers next, and it's nothing really new, it's just an application of the idea that you guys are working on.